Math 2312, Chapter 1, Functions, Section 1, Functions and Function Notation. Video 1, Definitions, Ways to Represent Relations. In this chapter we're going to learn about, or dare I say review, functions. And in each section there will be a series of videos covering individual topics. This way you can just focus on the topics that you need some extra help on. And the other ones you can just watch once and probably be done with it. In this first video, we're going to define some words prior to defining a function and look at ways to represent what are called relations. In math, a relation is a set of ordered pairs, typically written in parentheses with a comma in between. Granted, this pair is missing its second coordinate, but there are other ways to represent relations, as we'll see here in a moment. The domain is the set of first coordinates in a relation, and the range is the set of second coordinates in a relation. On the board, I've got the setup for 4 examples. Not all of the relations are complete because not all of the ordered pairs are completed, but we'll complete them as we discuss them. And we're also going to attempt to answer the question, what's the domain and range of each of these relations? Some of them we're equipped to answer now, some of them we're not. Let's start with the first way to represent a relation, which is in set notation. All that means is you write your ordered pairs separated by commas inside a pair of braces, making a set out of it. Now, in this particular set, I've set up only 3 ordered pairs, and each of them starts with a color: red, black, and brown. What I pair with them is actually irrelevant. I can put anything I want to complete these pairs. Several times, dare I say more times than not, in a relation, there is a relationship between the first coordinate and the second coordinate. Although technically, based on the definition, they don't have to have anything to do with each other. I have a particular relationship in mind between these ordered pairs' first coordinates and their second coordinates. For each second coordinate, I'm going to write a number that represents the number of letters in the first coordinate. In this first ordered pair, since the first coordinate is red, and red has 3 letters, I'm going to pair it with the number 3. Again, there doesn't have to be a reason why I'm pairing this 3 with this word. I can put anything I want over here. 3, 4, -7, pi, square root of 2, cosine of 15 degrees, or Tallahassee. Anything I want, really. But again, most of the time, the ordered pairs in a relation are paired for a reason, although it's not technically necessary to be a relation. That being said, if I pair each word with the number of letters in the word, then you probably already know that each of these ordered pairs are going to have 5 for the second coordinate, since black has 5 letters and brown has 5 letters. Another way to represent a relation is a table where each ordered pair is represented by a row if you have a vertical table. Tables can also be represented horizontally where each column represents an ordered pair. If you'll notice, the letters I've chosen here aren't the typical X and Y like a lot of people think when they see an ordered pair. The truth is, the first coordinate of an ordered pair does not have to be called X, nor does the second coordinate have to be called Y. They can be called anything you want. X and Y are just the generic defaults, but you may have a context where the letter chosen means something. For example, in this table, the first coordinate is represented by the variable t, whereas the second one is represented by the variable d. Do you know what 2 words I had in mind by selecting the variables t and d? For those of you who have had physics before, you could probably figure out that I'm using t for time and d for distance. In this particular case, I'm imagining a car traveling 50 miles per hour, and the question is, after so many hours, how far has it traveled? Well, if it's traveling 50 miles per hour, then after 1 mile, it's traveled 50 miles. After 2 hours, it's traveled an additional 50 miles for a total of 100. And then 150 miles after 3 hours, 200 miles after 4 hours. Of course, this is assuming that you're maintaining a constant speed and you're not making any stops along the way. There doesn't have to be a relationship between each pair or within each pair. Often there is. Another way to represent a relation is an equation, such as x equals y squared plus 1. Now, you might think that that's not a relation because by definition a relation is a set of ordered pairs and this is an equation. So how could this possibly be considered a relation? Well, the answer is the equation implies ordered pairs, namely ordered pairs that make the equation true, or equivalently solutions to the equation. For example, let's say I take the ordered pair 5, 2 and ask, does this ordered pair belong to this relation? So we'll put a question mark after it. Assuming that the first coordinate is x and the second is y, and we'll make that assumption, we could check it easily by substituting the 5 for the x and the 2 for the y. But it wouldn't take too long to verify that 5 is equal to 2 squared plus 1, therefore this ordered pair belongs to this relation. What if I reverse them? Would 2, 5 belong to this relation? Well, if we substitute the 2 for the x and the 5 for the y, we get an equation that's not true. 2 is not equal to 5 squared plus 1. That means that the ordered pair 2, 5 is not part of this relation. So although this equation doesn't explicitly list ordered pairs, we can use it to check if an ordered pair belongs to the relation by seeing if the ordered pair is a solution of the equation. Now, typically, we wouldn't just make an ordered pair at random and say, I wonder if that's a solution to the equation. Typically, we would generate such ordered pairs. In fact, I'll show you how to generate some. The easiest way to generate an ordered pair for an equation is to pick a value for one letter and find values and solve for the other letter. For example, let's say that x equals 5, and let's see what this implies. If we substitute 5 for the x, we get 5 equals y squared plus 1. If we subtract 1 from both sides, we get 4 equals y squared. And if we take the square root of both sides, you have to be careful. Why do you have to be careful? Because you might remember, especially if you've had college algebra, that when you square root both sides of an equation, you have to pick up a plus minus. In this case, the square root of 4 is plus minus 2. And of course, the square root cancels the square on the y. It's worth emphasizing that not all square roots pick up a plus minus. Here's a brief reminder from college algebra, whether or not you've had it. A square root by itself comes out positive by definition. However, if you have an equation, then you put a square root on both sides of it, that procedure says it's time to put a plus minus on one side of the equation. Again, for clarity, when you just square root a number, it's positive. But when you square root both sides of an equation, that's the time to put the plus minus in there. And if you'll notice, we have two solutions for the y, 2 and negative 2, which means that both 5, 2, and 5, negative 2 would be solutions to this equation, and therefore, these are two ordered pairs that belong to this relation. Are there more? Of course there are. How many? A bunch. Similarly, we could generate more pairs. In fact, if you wanted to be super generic about it, we could do the exact same thing we just did without substituting a number for the x. In other words, we can make what's called a generic ordered pair for this relation by saying, what would happen if I put in a number for the x and I started solving for the y? If I started solving for the y, I would subtract 1 from both sides, get x minus 1 equals y squared, break out the square root on both sides, and again, that's the signal to put a plus minus in. Nothing happens on the left, so we pick up the plus minus, and it cancels the square on the y, and we get y equals plus or minus the square root of x minus 1. Basically, by solving for y, I've created a formula that can generate as many ordered pairs as I want. Namely, if I pick a number for the x, there's two different values I could calculate for the y. The square root of x minus 1 or negative square root of x minus 1. And now I've created a way to generate as many ordered pairs as I want. So again, I could generate one ordered pair at a time, or in this case, two at a time, by substituting a value for x and solving for y. Or I could just solve for y and say, here's a generic way to crank out as many ordered pairs as I want. And by the way, the choice to put in a number for the x and solve for the y was somewhat arbitrary. I could have picked a number for the y and solve for the x. And I would argue that would be easier here, because if you were to substitute a number for y, and then figure out what x equals, this already says x equals. So in other words, if I had done this backwards, well, not really backwards, but the other way, and said, let me pick a number for a y, and now let me figure out what x equals, well, x is already equal to y squared plus 1. So I could use this template to generate as many ordered pairs as I want. The last way to represent a relation that we're going to look at, and I'm going to move it over here where I have some space, is a graph. Everybody should know what a graph is. Everybody should know x-axis and y-axis and origin and everything like that. So let's just say I put a graph that looks like this, a parabola opening to the side. If you don't remember what a parabola is, I'll go into more details when the time is right. This represents a relation. How can we justify it's a relation when by definition a relation is a set of ordered pairs? Well, the answer is every point on this graph represents an ordered pair. For example, if I pick this point, and I don't know what it equals, but let's just say, because I didn't mark up the x and the y-axis, but let's just say it's the point 5, 2. I know that's probably not to scale, but we can just assume that. By the way, if this were the point 5, 2 and this were symmetric, what do you think the point down here would be? Well, it's over the same amount, so it would still be 5, but if it's symmetric, then instead of up 2, it's down 2. What about this point over here? Well, again, without further information, we're just speculating what its ordered pair is. But let's say for the moment that it's 1, 0. On a graph that was generated from an equation, or a graph that's sitting on a coordinate plane that is accurately marked on the x and the y-axis, we could either calculate or estimate any point's ordered pair at will. So again, a graph technically is a relation because although it doesn't explicitly list ordered pairs, it implies them. Before we wrap up this video, let's see if we can pull out the domain and range from some of these relations. We can actually pull out the domain and range from all of them with the correct tools, but in this video we're just going to use the definitions that the domain is the set of first coordinates and the range is the set of second coordinates. In set notation, this is easy. You simply have to open up a set and write all the first coordinates. In this case, red, black, and brown. Not sure if that marker's coming across pretty clear. Let's try this blue one. The range is just the set of second coordinates, which in this relation are 3, 5, and 5. However, there's no need to repeat a value because it's redundant. Our second coordinates are 3 and 5. So domain and range is easy to pull out from a set of ordered pairs. And from a table, it's just as easy. I would argue it's easier because your domain and range are already separated. In this case, the domain is 1, 2, 3, 4. And the range is 50, 100, 150, 200. So in set notation and in a table, domain and range are fairly easy. For an equation and a graph, not as easy. Because remember, both an equation and a graph generate ordered pairs without explicitly listing them. So we can't just look and say, here's all the x's, here's all the y's. We would have to be a little bit more analytical in determining what are all the possible x values and what are all the possible y values here, and the same thing for this graph. And we are going to do that Some of it sooner, some of it later, but eventually we'll do it all.